Hey guys, I wanted to create this quick little video for you today to try to demonstrate how we can go about finding the energy that's included for something in a flame test lab. So I want you to remember a couple of things. First of all, we know that delta E, the energy, is going to be equal to Planck's constant h times c divided by lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. Now, a couple things we also need to remember. We need to have agreement. So when we're talking about the speed of light, c is equal to 3.0 times 10 to the 8th meters per second. And our lambda, therefore, we need to make sure that we're keeping in mind that our lambda has to be measured in some number of seconds. No, not some number of seconds. What am I talking about? It needs to be measured in some number of meters because we have to have agreement. So when we're talking about yellow, okay, we can say that the wavelength of yellow light is somewhere in the neighborhood of, let's say, 500 nanometers. Okay, so the first thing we need to do is to understand that the nanometers do not agree with our meters up here the way that we need to have it. Okay, so how do we go about converting from nanometers to meters? Well, what we're going to do is we're going to say, all right, 500 nanometers are what we're starting with. This is that dimensional analysis we worked on at the beginning of the year, over 1 times. The representation I gave you today was for every 10 to the 9th nanometers, you would equal 1 meter. So now what this happens is our nanometers are going to cancel out. We're going to be left with 500 times 1, which is going to equal 500, with the unit being meters, divided by 10 to the 9th. Okay? Now, we have our trusty little calculator over here on the side, and because we have that little calculator on the side, we can easily say, all right, 500 divided by, open parentheses, 10 raised to the 9th, close parentheses, equals 5 times 10 to the negative 7th. So I want you to keep in mind that this is 500 nanometers that we started with. 500 meters divided by 10 to the 9th is going to give us an equivalent 5.00 times 10 to the negative 7th meters. Okay, this is going to be a really important thing for us to keep in mind, because this 5 times 10 to the negative 7th meters, we're going to have to remember to put into place for this equation over here. Okay, so now just a couple of other things for us to keep in mind. I'm going to switch colors now so we can see that we're going on with a different equation. Okay, so that's how we converted our nanometers into meters so that we had agreement here. So now we want to find delta E. We know that delta E is going to equal h, which is Planck's constant, times c, which is the speed of light, divided by lambda that we just figured out in meters. Okay, so we know that our h is going to be equal to 6.626 times 10 to the negative 34th joules times seconds, because that's the unit, times the speed of light, which is going to equal 3 times 10 to the 8th meters per second. And that whole thing is going to be divided by the wavelength that we got in meters, which is 5 times 10 to the negative 7th. So 5.00 times 10 to the negative 7th meters. And so now we can go ahead and understand that that's going to be equal to that delta E that we just figured out. All we've done is substitute in. And so now we go back over to the calculator one more time. And what we can say is, open parentheses, 6.626 times 10 to the negative 34th. So we can say EE negative 34, close parentheses, times, open parentheses, 3 times 10 to the 8th, which is 3E8, close parentheses, equals. And so what we're left with now is we can see that delta E is going to equal the numerator of 1.9 we'll call 99 times 10 to the negative 25th. And now it's going to be a really long convoluted unit called, not really long convoluted, but it's going to be a unit because our seconds are going to cancel here. You can see the seconds cancel with the seconds here. Joules, whoops. How do I undo that? Got this new little program here, help me out, and I don't know what I did. Hopefully I can get this figured out. Not wanting to undo here. There we go. 1.99 times 10 to the negative 25th, and our unit, make sure we got the right pen up, and our unit is going to be joules times meters. Okay, and now we're going to take the whole thing and divide that whole thing by the 5.00 times 10 to the negative 7th meters. So now your meters will cancel out, and so what we're going to be left with is going to be back to our calculator, that 1.99 times 10 to the negative 25th. We'll divide that by, open parentheses, 5 times 10, 5e, negative 7, close the parentheses, enter, and what we're left with now is a value which is going to be equal to 3.98 times 10 to the negative 19 joules. So when you take a look at this, what this shows us here is that when we perform this calculation, remember there are a couple things we had to keep in mind. First of all, we had to make sure we had unit agreement, and so we wanted to make sure that our wavelength up here matched our speed of light, so they both had to be in meters. Once we had that all set up, which is what we did over here, it was just simply substitute and solve. Planck's constant is always going to be 6.626 times 10 to the negative 34th, and I'll always give that to you on a test. The speed of light is always going to be 3 times 10 to the 8th, which I will also always give you on a test, and now all we had to do was substitute that other piece of information, which was the wavelength. So we can really see that the energy change for an electron was completely and 100% devoted to or contingent upon that that wavelength exclusively, because the other two things are constant. So I'm hoping this little video helped you out. I'm hoping you were able to figure out exactly what you wanted to do here, and I'm hoping that when you are able to work your way through this, you'll be able to use this to answer your questions, and it'll be all set for you. Okay, thanks.